On screen now is some of the equipment that's going to be used for this laboratory exercise. First of all, the hydraulic bench made by Armfield. It's an F1-10 hydraulic bench. This is the device that we're going to be using to send flow through the pipe rack. The way that flow rate is quantified on the hydraulic bench is that there is a tube that indicates the level of water in the wet well in the hydraulic bench, and so the water level will rise in the tube, and the time that it takes to accumulate a certain volume inside of the wet well will be noted, and that is how you quantify the flow rate. The flow rate is controlled from the bench. There's a valve that's pictured there on screen that allows you to increase and decrease the flow rate. That valve will be wide open during this experiment, and instead of adjusting the flow rate with that valve, we'll be adjusting the flow rate with the valve on the pipe rack itself. Okay, the pipe rack, also manufactured by Armfield. It's a C6-10 fluid friction measurement apparatus. This pipe rack has several different diameter tubes, and in this experiment we won't be using the pipes themselves, but we'll be using a number of the fittings. And we'll go through each of those fittings during the experiment itself and showing the data collection. There are 3 primary pipe pathways that are used in quantifying the flow rate through these different fittings. The third and final primary component in this experiment is the device that we're using to measure the pressure differences between the upstream and downstream tap on the fittings, and this is a Comarch C9555 pressure measurement device, and it's connected to each of the taps with simple plastic tubes that allows a difference in pressure to be measured. A couple of auxiliary items that are shown there. You can see that there is the red bucket. The red bucket is used because it's important to purge air out of the lines that are connecting from the tap to the pressure measurement device. If little air bubbles are in that, then there can be additional fluctuation and introduces an element of error that we want to eliminate. And so when a tap is plugged in, I'll periodically check for air in the lines, and if air is observed, then it'll be purged out of the lines into the bucket. Also, you'll notice that there is a yellow pan, and that's because the pipe rack leaks. You can see duct tape has been used to sort of direct the leaking downward rather than spraying all over the place. To capture the leakage with the pan, and the green towel is to clean up additional drips. From the safety perspective, some of the things we have to keep in mind as we're performing this lab experiment is, first of all, there's electrical energy involved. You can see that it's plugged into a hanging power cord, and so we're going to want to always be cautious to make sure there's no frayed cords or that there's any sort of a shock hazard associated with standing in cooling water and handling the electrical components that we're going to be utilizing. Other safety issues is that the cord is a possible trip hazard. I'll try and tuck that underneath the bench to the extent that it's possible, but still we have to be aware of our surroundings to make sure that there's no trips or slips, because there will most likely be some additional water spraying out of the bench or dripping from the pipe rack. We have to be vigilant to make sure that none of this slippery concrete gets wet, because that could cause a slip hazard. One other final thing is that this pipe rack is itself a little bit top heavy, and so make sure not to push on it or pull on it. As I'm putting in the pressure measurement tubes, I'll try and support that with my hands. So that concludes the overview of the equipment and a little bit of a safety tour. So what we'll begin now is we'll go through measure the flow rate, and rather you will be observing the conditions that allow you to quantify the flow rate, and then we'll take measurements at each of the fittings that are in this pipe rack. Okay, the bench is turned on, and the flow rating, the flow setting is fairly high. The bench could be turned a little bit higher, but then that just causes a lot of splashing outside of the wet well, and so I turned it down to a high but not extremely messy setting. Contrary to my previous suggestion that we wouldn't be adjusting the flow rate with this valve, looking at the data sheet again, I realized that we're supposed to quantify the gate valve with it fully open. The K values that I have provided for gate valves are a gate valve when it's fully open. And so what I've done is I've opened up the gate valve here in setting 1, flow path A. The gate valve is the one on top there. We're going to be trying to quantify what sort of energy loss there is through a variety of different fittings, including this gate valve, so it's all the way open. Therefore, in order to quantify the flow rate, I did have to use the valve that's internal to the bench. That doesn't change in the calculations that you're going to be doing. I just wanted to mention that for sake of completeness. Now, when I drop the ball inside of the wet well, it's going to allow water to begin accumulating. You'll see it on screen. It's going to first go through these slow flow rate graduations of 0 to 6 liters, but you will note the time that it passes the 0 mark on screen, and then you're going to measure how long it takes to accumulate 25 liters inside of the wet well. So I'll go drop the ball on that now. You should have a stopwatch handy, some sort of a way of measuring the time, hopefully more precise than just looking at the time counter on the screen as you're watching this video. All right, I'm dropping the ball. So the water has begun accumulating in the lower wet well, where the water level rises faster because of the reduced cross-sectional area, but now it's about to cross the 0 mark there. I'll let you indicate the beginning with your own stopwatch. Meanwhile, I'm going to be collecting data during this experiment just for my own purposes. I won't provide that data to you, but I'm curious to know what sort of results I get. Hard for me to resist an experiment. All right, so now what you should have done is observed how long it takes to accumulate a certain volume. I'm going to open the plug on the wet well now. We've quantified the flow rate, and since I'm not going to be changing any of the fittings as we take pressure measurements, the flow rate won't change. If I change the position of any kind of a valve, then I'd need to re-quantify flow rate, but that's not going to be happening. Let's just tour briefly through which fittings are going to be having their pressure quantified. First of all, we're going to go through the 45 degree Y. And let me bring that up on screen here, the 45 degree Y. And you can see the tap upstream and the tap downstream. We're going to be going in a straight line. We haven't yet directed flow sideways out of that. So that is the 45 degree Y. Item 6 on your figure, included with the lab handout, is the long radius 90 degree bend. Next, we'll move on to the ball valve. The ball valve is here. The ball valve is currently open. Next will be the 90 degree T. The 90 degree T is shown on screen. With the 90 degree T, we're going to be quantifying the energy loss for flow that's going straight through a 90 degree T. So it won't, will be again being in a straight line. The upper and the lower taps are the ones that are going to be measured here in just a moment. Okay. The next fitting is the, I'm sorry, I've mixed something up. We've missed the 90 degree miter. Okay. The 90 degree miter is here, this very sharp edge transition. So we'll also be quantifying the 90 degree miter, the T, which we already saw, and then the, whoa, I'm gonna get dizzy watching this video. All right, that is the short radius 90 degree bend, and finally, the energy loss through the gate valve, which is that upper valve, and you can see the tap on either side of it. Okay, so we will now begin measuring the flow rates at each of, the pressure drop at each of those Okay, you can see that I've mopped up some overspray out of the bench, trying to keep things so that it's not too slippery. When the taps are plugged in, you have to listen for a distinctive snap. I'm going to hear that snap, and it will tell me that it's in. I'll take the downstream snap. Go ahead and get that plugged in. Hear the snap.
and I see that there are air bubbles in the line, and so I'm going to purge these lines of air. All you have to do is disconnect it from the pressure meter, and water will flow into the bucket. I'm going to raise it up to try and coax those air bubbles out of the tube. I can see there's actually a pretty long stretch of air in there. Really improve our accuracy considerably to make sure that there's nothing but liquid in there. And I can just plug it back in and it's good. Same thing with the downstream tap. I want to make sure that I get all of those air bubbles up. So I'm lifting the tube high, allowing the air bubbles to rise. Okay, they're gradually making their way to the top of the tube. And as soon as I see that that air bubble's out, then I'll just plug the plastic tube back into the pressure meter. All right, it is in. Okay, you can see that the pressure gauge is jumping around a little bit. What I need to first do is make sure that that pressure gauge is zeroed. So I'm going to close the downstream valve so that there's no flow going through the pipe. I'm going to push the 0 button so that it's been zeroed. Open that valve back up again. Now, since that valve has just been exactly back to the same position as before, we can expect the same flow rate. The negative pressure measurement means that there's a pressure loss through the fitting, which is exactly what we'd expect to see, is less pressure downstream than there was upstream. And so what you should do, what you need to do is take some pressure measurements there. It's jumping around a bit, and the way that we handle that and overcome it is with a temporal average. So you'll see several different values. Enter 5 or 6 or 10 of them into your calculator, and then take the average of all of them. I'll do the same. I'll write down some values on my page, and later on I'll take an average so that I know the average drop in pressure through this fitting. We're working with the 90-degree Y, so writing down data. When the pressure is small like this, it's particularly sensitive to these rapid variations, so hopefully we'll get better data with some of the other fittings where there's more energy loss. All right, hopefully that's been enough for you to gather some data. Of course, you can replay this segment of the video again if you want to get different data or more data. So that's our 45-degree Y. Next we're going to move to the long radius 90-degree bend. Rather than unplugging the tap that I've already got in at the lower position, I'm just going to unplug the upper one that's here and move it to this location. Now, swapping what's the upstream and the downstream is going to mean that I'm going to have positive pressures now instead of negative, but that's okay. We still know it's a pressure drop. Let me go ahead and do that. All right. I'll inspect to see if there's any air in the lines, and it seems like I didn't get any air in the lines, so I'm in good shape there. Let's again get some pressure measurements. I'm going to mop up a little bit more of this overspray, particularly off the instrument, the pressure instrument. All right, let's take a look at some of the data that we're getting through this device. Seems like we're losing a little bit more pressure through here than we did through the other one. I'm going to double check the 0. So closing the valve should, once it stabilizes, take it down to 0. It is. That's good. Open the valve back up. And let's take 5 measurements so that we can get an idea of the average pressure loss through the long radius 90-degree bend. Okay. Now all of this is still at the same flow rate that we quantified before. Okay, next moving on to the ball valve. The ball valve is here. I'm going to have to move both of the pressure taps. Okay. I've got those taps in, and I am seeing a pressure differential. We'll make sure that it is still zeroed. Let me move that tube out of the way. And we can see that the pressure is jumping around. I'll close the valve, make sure it's zeroed. Hello. I guess that means zero. All right, so we'll gather some measurements here that we can use as our average differential through the ball valve. Turn the meter back on. Okay. All right, so I've gathered 6 measurements there. You could potentially get even more. Next, on to the 90-degree miter. So the 90-degree miter is this one. Again, I'll just switch one of them since I'm already plugged into the upstream tap. I'll move that one there. We are plugged in. We'll find the pressure differential. Wait for it. There we go. All right. Let me prop that up so that it's easier to see. I think that it's at a bit of an angle there. Is that a little easier to read? All right. Gather some data. This is the 90-degree miter, fitting 14. All right. "90-degree T is next. 90-degree T, we're already plugged into one of them. Let me go plug in the other. I'm going to visually inspect the line to see if there's any significant air bubbles that need to be purged. Again, it looks like oh, I do see one. Actually, I see 2, so I'm going to go ahead and purge those. Good data is the essence of experimentation. All right. Purged. I have to flick it to get these ones to move. There they go. Come on. These ones are stubborn. I'm not getting much flow through this fitting. Try plugging into a different tap. I don't understand why I'm not getting more flow than I am. Well, now it's going. It might be that this tap is got mineral deposits or something behind it, because when I plugged in, I wasn't getting any flow from it. So we may not be able to quantify the flow rate through this bend. Let's just see if there's any data when I turn off, any difference in the data when I turn off the flow versus when it's running. Okay, so I'm turning on the pressure meter. Let me tip it up again. Okay, we are getting some pressure measurements. Let me close the valve so that there's no flow, and that should go back down to 0. Okay, so closing the valve. Not quite 0, let me 0 it. Okay, it's maintaining 0. I open the valve again to its original state. Let's go ahead and gather the data, but then put maybe an asterisk next to the 90-degree T that I wasn't able to get flow through that upper tap. And we are measuring a pressure differential, but it might be that whatever hole there is between the tube and the pipe is very small, and so there was a low flow rate, but I can still measure a pressure differential. Anyways, let's get some of this data. Okay. Next, the short radius 90-degree bend. All right, I will plug in the taps to it. Now, each of these fittings that we're doing thus far are going to be energy losses, and so really its pressure is decreasing. I haven't been real meticulous in noting which tap is the upstream tap and which is the downstream tap, simply because I know that all of these are going to induce an energy loss. And again, I've got a air bubble that I need to get rid of. So what I'm saying to you is that the sign of all of these, it's going to be a pressure loss, and so it's a head loss that's occurring. In each case, whether the sign on screen has been negative or positive. All right. Okay, I think I'm clear of significant air bubbles. So. Very low energy loss on this one. Let me turn off the flow so that we demonstrate that the instrument is still zeroed. Okay, so flow rate off. Ironically, it's not well zeroed. Okay, it's 0. Turn it on. Okay, we are seeing some pressure difference through here. This is the short radius 90-degree bend. And finally, we're moving on to the gate valve. Gate valve, there we go. Okay. Plugged in the gate valve, checking for air bubbles. Line seems clear of air. See how much pressure difference we're seeing. Again, I will cancel the flow to see if the instrument is still zeroed. That's difficult to read. Let me see if I can get a little bit better angle on it. Okay. Closing the valve. Zero the device. All right, the device is malfunctioning. Let me turn it off, turn it on. Zero the device. Okay. I'm going to have to pause the video and see if I can troubleshoot the pressure measuring device here. All right, there was some crud, I think that's the technical term for it, behind these taps screw in. It's just like a threaded plastic, like a vinyl or something that screws in to these holes in the pipe, these mounts. And so I cleaned it out, and we'll plug in the tap and see if it works again. So safe for sore eyes. Previously, no water was coming out. So now that we're getting water out, we should be able to get a pressure measurement at the gate valve. Previously, the instrument wouldn't zero, and that's because one of the sides of the device wasn't measuring pressure at all. So if I close the valve and the flow stops, it is now holding a 0 or pretty close to it. And I open back up, and we're measuring a pressure difference. Now, I did turn off the bench for just a moment, but I didn't change any of the valve settings. I left the bench flow setting the same. All the valves are as previously, and so we will assume that the flow rate is the same as was quantified previously. So now this is the final fitting on pipe path A, gate valve, item number 21. So measure the flow difference, the pressure difference there. Okay. The first of the fittings that we're going to characterize pressure loss through here on pipe path B is the 45-degree elbow. I'll connect the taps. Now, I'm going to have to quantify the flow rate again because I've got a different path, a different flow path. I previously have been using that valve on the lower pipe. Now I'm going to open up the valve above it. This is open. And now that I've got water flowing through a different pipe, our flow rate's going to have to be quantified again. Another change I'm going to make is that water has previously been going through the upper gate valve, and now I want it to go through the lower globe valve. And so I'm going to open up the globe valve all the way. The globe valve is open, and I'm going to close the gate valve. All right, so you can just sort of audibly hear that the flow rate has changed slightly. Let's go ahead and quantify that flow rate. This is the flow rate we're going to use for flow path B. I'll drop the ball. Have your stopwatches at the ready. And I'm just clearing my stopwatch so I can follow along at home. Okay, you need to indicate a certain volume collected in a certain amount of time. So it doesn't matter if it's from 0 to 25 or from 1 to 23, whatever you know that volume increment is, and the corresponding time it took for that volume to accumulate in the wet well at the bench. I can see some of you really concerned with accuracy, doing a frame-by-frame analysis, trying to figure out when it crossed a certain threshold. All right, I'm going to open back up that plug in there and note the time that it took and the volume of accumulation in my own notes, and we will move back over to the 45-degree elbow. Okay, so again, we're going to be characterizing the pressure drop through the 45-degree elbow. We'll move over here to the instrument, pop it on, zero it, and begin taking some data. Just turn on, fill the flow rate momentarily, zero the device. It's holding at zero, more or less. We can write down several values with which to calculate our average pressure drop through the 45-degree elbow. Next, we'll be doing fitting number 22, which is the 90-degree elbow. Here's our 90-degree elbow. We'll plug into it. All right, I'm plugged in. And I will zero the instrument, and then we'll measure the pressure drop through there. Looks like this is going to be a big one. Okay, fill the flow. Make sure the instrument is reading zero. All right, it is not, which may mean that once again we've got a plugged valve. So let me pause the recording and troubleshoot. Okay, only one of the tubes is leaking water. They both should be when they're taken off the pressure measuring device. So it looks like we've got some values there with which to work. Okay, I'm inspecting for air bubbles and don't see any.